Welcome everybody. Thanks Eoin for accepting our invitation to talk here today. Eoin is a lecturer at the Atlantic Technological University Sligo in Ireland. He was a PhD from Imperial College London in string theory and mathematical physics. Following that, he was a postdoc at Korea Institute of Advanced Study, then Oviedo and Sunnybrook. After that, he became a research professor in Korea at Asia Pacific Center for Theoretical Physics and Sogang University, where his interests shift from the high-energy physics to the astrophysics cosmology. Today, he will present Is H not a constant in lambda-Godal matter cosmology? Eoin, you can start, please, when you're ready.
Okay, thanks for the opportunity to present this. This is a controversial talk. So the tone, dark energy, physicists have been thinking about dark energy for a long time. Theoretically, it's a very, very fishy thing. It would be nice to get rid of lambda. Okay, so this talk will go in that direction. And basically, I'm going to ask, is H0 actually a constant in the Lambda-CDM model? And there's this beautiful quote of Weinberg. It's actually a book review. I forget from where, but it's basically it's an evaluation of Thomas Kuhn's work on structure of scientific revolutions, and he's just commenting on how paradigm shift comes about. So, we've got normal science and we're following normal science, and that's what a lot of cosmology is following normal science, especially this, the stuff, large scale structures. We want to place constraints on W. That is basically a program of normal science, and you basically whittle down W and you basically make sure it's -1, you confirm the Lambda-CDM model. What's happened in the interim is we've got anomalies in data. Like, while there's been a whole lot of experiments who have geared up for large scale structure, these anomalies have come through, and then we're debating whether or not they're, new physics, missing physics, or are they systematics. And the debate is going over and back, and I'm tired of the debate, and I'd like to finish it. So if you finish this debate, then we're looking at new physics, we're looking at some sort of paradigm shift, we're looking at evolution. But at the moment, there's lots of alarm and confusion in the community. I just think this quote sort of sums it up. I don't know what's going to come out, but I'm going to give you a claim and a picture of what may come out, and then you can try and prove me wrong. It's as simple as that. Okay, so in science, so cosmology for me is an endeavor that you pursue in science. Cosmologists like to put it inside physics, and physics, of course, is within science. And if you're doing science and you work on dynamical models, your models have fitting parameters. You're assuming that those fitting parameters are constants. If you fit them in epoch A and epoch B, and you find that you have different values for the fitting parameters, that by definition is a bad model. So a good model is a model where your fitting parameters are constant. This is just a very, very simple definition of what is a good model. Now, Lambda-CDM is a dynamical model. We just basically replace time with redshift, and redshift is basically the proxy for time. We've got these anomalies, H0 and S8 tension. They point to early versus late universe mismatches. Now, early universe here means high redshift. Late universe means low redshift. It looks very obvious. There seems to be a mismatch at redshifts. Systematics aside, this looks like the expected telltale sign of redshift evolution, which is essentially evolution in time, and your model is breaking down. And the main point, if you take nothing from this talk, it's this point here. If you believe the tensions are physical, some people believe they're systematics. If you believe they're physical and you're trying to model them, there must be redshift evolution in the original model, the Lambda-CDM model, at some redshift. That has to happen. If you just end up with a contradiction if there is no redshift evolution in the Lambda-CDM model. It just says that your model is fine, and that basically there's systematics in maybe cosmic shear, or there's systematics in local H0 determinations. That's all it says, right? Because the model is fine, right? So we have to have redshift evolution. Parameters defined today at z = 0 are integration constants. If you're a mathematician, that's what they are, right? So this is a mathematical statement. When you say omega n 0 is defined at z = 0, or H0 is defined at z = 0, that's just saying from the perspective of mathematics, this is an integration constant. But that's not an observational statement. And you need to check, that there's no conflict between mathematics, your modeling, and the observation on the other side. Once you have conflict there, you have a bad model. So this is the basic picture. So these are the Friedman equations. Cosmologists have all seen these many, many times over. We teach them to undergraduates, maybe even in first year. This is a first order differential equation. On the right-hand side of this equation is there's rho and p. Now, it's impossible to solve these equations unless you tell me how p is related to rho. So once you do that and specify that relationship, which is basically an equation of state, you can solve these equations. Now, so basically, so W of z, I'm just going to basically say everything's just a function of z. I'm going to put it in an overall function. And basically, once you give me that guy, you have to give me that guy. Once you give me that guy, I solve the equations and I have a model, right? That's the general picture. You really have to specify that before you can solve the Friedman equation. So W effective of z, or your equation of state, or overall equation of state, effective equation of state, is just your model. It could be Lambda-CDM, it could be something else. Now, right, let's see. So with this effect, once you've specified this guy, which you have to put in at the beginning before you do, any comparison with observation or anything like that, you specify that guy, you integrate it up. H0, you need at least one you need to specify h of z at some z to solve that first order differential equation, which you do, and you basically say there's a constant h0 at z equals 0. So once you do that, you end up with this equation here. W effective of z is just some generic function of z that you've fixed. The output of this is the left-hand side is essentially the Hubble parameter. This guy here is an overall factor. That's your integration constant. For any FLRW cosmology, that's what you get. This structure, h of 0 times some function of z. Now, all I'm going to do is rearrange that. And I'm going to rearrange this to start a discussion about what cosmologists are actually doing conceptually. What cosmologists are doing conceptually is that they've put in by hand a theoretical assumption, which is this W effective of z. That, you cook up. We started with basically, we have radiation and we have matter, right? And we found that that wasn't sufficient. We found that we had to add various other things like dark energy, etc. But you essentially put that in. There's some physical considerations that basically specify what this function or family of functions should be. And then you're going to go off and compare it to h of z, which a priori is unknown. You can be extracted directly from observations. And there are, parts of the cosmology community or members in the cosmology community, certain groups who advocate basically reconstructing h of z directly from observation. And you can do that as well. There's just no physics in reconstructing functions from observation because you haven't put in any inputs, right? We're not learning anything about physics that way, right? But in principle, that's what's happening, right? We have two functions, one you put in by hand and the other, which is unknown, but we extract it from data, but we assume that there is a function there. And there's no reason in the world for these two functions to agree. Their z dependents can disagree. Now, this W effective of z it's not just one function, it's a class of functions in the case of Lambda-CDM. So basically, it depends on matter density. It has a matter density parameter, right? But still, you can still imagine a mismatch where, I go off and I compare that with h of z, and I find that the z dependence is not the same, and h0 then just has to pick up z dependence. There's nothing you can do about this. So whenever the h of z, this unknown, or this parameter we're trying to extract, let's say function, we're trying to extract from observation, and W effective of z disagree, and they must disagree at some precision. There's no way you can basically pull a function out of midair and hit something that you just don't know what it is. This is just impossible, right? When they inevitably disagree, basically your h0 starts to run. That's basically what happens here. And then everything that talks to h0, all your other cosmological parameters, they're also going to pick up redshift dependence. And there's nothing you can do about this. So when the issue talks about multiple h0s, this is essentially the back end to that argument, right? If your model is breaking down, you expect h0 not to be a constant, but you expect it to evolve with redshift. The basic idea, right? Now, is there any questions about this, right? Model breakdown and why you would be interested in evolving cosmological parameters? Sure. If not, I'm going to tell you a little bit.
One thing that I'd like to understand, it's Vivian here. Nice to meet you.
Hey, Vivian.
In principle, and you're perfectly correct that if you assume the shape of W from a theoretical background, and there is deviation in H of Z essentially that are not captured by WF, then it's not going to pick up. This is fine, but people have also reconstructed W. I mean, instead essentially of reconstructed H, just let the data tell you what W
Right,
is.
good, right. No, and I have a response to that. So basically, typically when people reconstruct H of Z functions, those are, and people use this label all the time, those are model independent. There's no degeneracies there. Any model has an explicit degeneracies, right? So in the Lambda-CDM model, H0 can go down and omega m can go up, while a particular combination stays the same. And that particular combination is omega m H squared. That basically fixes the high Z part of the Hubble parameter, right? So when cosmologists say, oh, I've reconstructed H of Z directly from the data and I see it agrees well with Lambda-CDM, that's fine. You've shown that the Hubble parameter is the same. But you haven't shown that the parameters, the fitting parameters are the same, that there's no evolution there. Because I can give you a scenario where basically, and I'm going to give it to you in this talk, basically H0 is decreasing, omega m increases, and the combination can be more or less the same, and you just wouldn't see it in any of your reconstructions.
Okay, well, just let's see.
So if it's one thing to say the Hubble parameters for my reconstructed Hubble parameter and the Hubble parameter for my chosen model are the same, but that doesn't preclude evolution in the fitting parameters in the model, right?
Sure. No, I understand. It's a constraint.
So I just want to.
And
I think that answers your question, though, right?
Maybe. Show me what you have afterwards. But I guess my claim
we'll
is
get
just
into this. We get into
right.
this.
Okay.
So Lambda-CDM, right? I've only been studying cosmology for a few years, so some of this was very surprising to me, and now I see it again, and I get comments from cosmologists, and it's less surprising. But I still think there are cosmologists out there who will find it surprising, right? If you're looking for evolution in fitting parameters in the Lambda-CDM model, what I'm talking about is H0 and omega m0, right? And whatever else you have in the model, right? You want to isolate a subsector of your model to make it as simple as possible and check for evolution there. If you find no evolution, you're okay. You can sort of say that subsector of the model is fine. Now, in the late universe, you can go after H0 and omega m just, through Hubble diagrams and anything you can construct in the late universe. It's a very, basically the Lambda-CDM model, which, can be quite complicated in the early universe. It reduces to essentially a 2-parameter model at the background level in the late universe, and one can go after this guy and look for evolution there. So that's the basic game we're playing. On the left-hand side here, I've basically got some mock DESI forecasted data in H of Z, and on the right-hand side, I've got mocks in DA of Z. This is taken from the DESI paper. So you can see the quality of the data sort of depends on which tracer you're in. Sometimes it jumps as you go from one observable to another observable. And at high Z, the key point here is what I'm going to be doing is interested in basically redshift bins and moving up in redshift to see what happens. And at high Z, you expect your Hubble parameter just to be sensitive to this combination. So Vivian, this is related to what we were discussing just now. I can give you an infinite number of values of H0 and omega m that basically where this combination would be exactly the same.
Sure.
It's fine, right? Just wouldn't see it in your Hubble parameter at high Z, right?
Absolutely. But what matters is the redshift dependence. So it's not just the fact that you're focused. If you just focus on, anyway, show me what you want. But
right. So let's go a little further, right? So this is very simple stuff, right? So what this is A on the left-hand side is more or less your dark energy density in the Lambda-CDM model, flat Lambda-CDM, and B is essentially the matter density, more or less, right? Now, and what I'm doing is breaking up this data set into 4 bins. So the bins are between 0 and 0.8, 0.8, 1.5, 1.5, 2.3, 2.3, 3.6. The data quality in each is more or less the same, right? And here I'm only doing H of Z constraints. So the D of A I'll discuss in a bit, but the H of Z constraints are there. And we know what to expect. We sort of expect that this particular combination will be constrained and the other combination is going to be unconstrained. And that's what we find, basically. As you go up in your redshift bins, you find that, any constraint that you had on your dark energy sector becomes, the distributions broaden. So yeah, let me explain what the distribution.
Is this the fake DESI data?
So what this is, George, is basically, yeah, I was a bit quick. So I've done 10,000 mocks of Planck Lambda-CDM, right? And then I fit back the Lambda-CDM model in redshift bins.
To which data?
And they're just best fits.
Yes, but to which data? What is the data?
It's DESI mock DESI data.
DESI mock. Okay, thank you.
So the forecast, so the errors are fixed by DESI. It's the Planck Lambda-CDM model otherwise, right? The underlying cosmology is Planck Lambda-CDM. But basically, I'm just sort of saying that, you know, as you all expect, if I start cutting out the low redshift parts of the data, then I become insensitive to dark energy density. And then my constraints basically on the matter sector, or this combination, this particular combination, H0 squared omega m, they basically contract, right? So I can only specify this combination, but not really that combination there, right? Now, when you translate this over, these are exactly the same. That's basically what would happen in A and B. If you basically translate that into the parameters you were actually fitting, which was H0 and omega m, what you find is basically as you go up in the redshift bins, you find that these non-Gaussian tails emerge in omega m. And basically there's a shift in the peak, right? Now, this puzzled me for a while. The non-Gaussian tails are sort of obvious. As you go up, you're becoming, you know, there's a general insensitivity that's sort of cropping in. Let me sort of explain what is going on here in a few different ways, and then hopefully we'll all be on the same page. So if we go back to this, as I go up, this is H of Z constraints. So they really are only sensitive to this combination here. Now, what that means is as I, basically, translate back into H0 and omega m, there's an infinite number of values of H0 and omega m that would give me exactly the, the same combination of B. So B is well constrained, but in principle, H0 and omega m are just completely unconstrained, right? So what this distribution is actually doing is it's flattening. It has to flatten. It has to go towards a uniform distribution as I just, go up in redshift bin, right? So I haven't normalized this thing, right? It's not normalized. So actually what's happening is these peaks are actually decreasing, and then the configurations are moving out towards larger values of omega m, right? But there still is a peak there. So I injected something at 0.3, and that peak is moving. Now, what surprised me was the movement. Now, the movement is easy to explain in terms of a projection effect. So basically, what actually is happening, one of these is H of Z, and one of them is dA of Z. I forget which is which, but it's more or less the same. You have a degeneracy here. You have a banana, a curve, basically in the H0 omega m plane. And basically, as you go up and cut out the dark energy sector and go up further in redshift, that banana just stretches. Okay, and so what you're doing in any given, say in this direction here, is you're just basically piling up configurations here. And those configurations are then basically going to force your omega m peak to smaller values. Right, and you see the same thing with, you'll see the same thing with H0 as well, right? So basically the omega m's will stretch in this direction here, and then that'll force H0 to go in, well, we'll force H0 to go. Let's see, think about this. Yeah, I don't know if I can think about this in real time, but anyway, omega m is basically going to, your peak is going to be shifted to lower values. That's what's going to happen. H0, it appears to go in the opposite direction towards higher values. They're essentially anti-correlated, right? Now this was only H of Z, whereas one of these is H of Z. One of them is dA of Z constraints. So they're different types of constraints, but we more or less seem the same trend, that there is basically a shift in the peak in omega m distributions and non-Gaussian tails. And you can attribute this to degeneracies, but those degeneracies are broken by combining H of Z and dA of Z constraints. And so there is a picture in cosmology that I need to combine low redshift and high redshift data to break degeneracies, but that's not true. I can give you mock data where I completely cut out the dark energy sector, and provided I combine D of A of Z with H of Z, no matter which bins I'm in, this is what the bottom plot is here on the right-hand side, that basically I always recover the input parameters and they're beautiful and Gaussian. And what is going on there is that basically dA of Z is sensitive. dA of Z is basically the integral of 1 over H of Z. Now, what you can think of that as a weighted sum. And because h of z is an increasing function of z, that's far more sensitive to the low redshift part of your data. Like even if the data isn't there, it basically is a weighted sum that is sensitive to low redshifts, and it becomes less sensitive at high redshifts, right? So, you know, small variations in high redshift data don't really affect it so much, but it is very sensitive to variations in the low redshift sector, right? So this to me is a very surprising result, and this is in this paper here. But it sort of tells you that, yes, if you start with mocks, and if you have D of A and H of Z data, and you construct probably enough of the mocks, that no matter how far you go up in redshift, even if you went up to, you know, beyond redshift of 2, you should always be able to recover your input parameters, provided you always have those 2 constraints, because they seem to complement each other in the flat Lambda-CDM model. And again, there's only 2 parameters. It's, you know, H0 and omega m, and roughly you can think of these as A and B. A is basically sensitive to the dark energy sector, and B is sensitive to the matter sector, right? But if you only have constraints in H of Z, like cosmic chronometer data, or, you know, constraints that are sensitive to dA of Z or dL of Z, which is proportional, right? So type 1a supernovae or quasars, then there's nothing to guarantee there's no evolution in those samples, right? You know, if we see evolution in the PDFs, even in mocks, then in real data, you know, all bets are off, right? And just to point out, these non-Gaussian tails are there. So there's no, you know, you can easily get large values of omega m at high redshift. Doesn't have to be 0.3. And the most probable value, actually, this guy is shifting this way because it has to flatten, and that's a projection effect, whatever you want to call it. But the most probable value is not 0.3. It's shifted down to 0.2, and it gets shifted below that. Now, of course, the peak is decreasing, right, as you go. It just wants to become flat. So I think cosmologists get sort of shut down when they hear the word degeneracies. But let me explain what a degeneracy is to somebody who's more, well, who, you know, has a strong mathematical background, right? The degeneracies just place you on a curve in the H0 omega m plane. That's all they do. You're on a banana, right? They exist. They don't fix H0 and omega m for you. You still need to fit the data to determine where H0 and omega m are. But I agree with cosmologists that the errors are large. Once you run into degeneracies, you can have large errors, right? But this is no reason to sort of just discount them. This banana curve stretches with effective redshift. That's what's happening. It's basically just going like that. This largely explains the non-Gaussian tails. But I mean, the fact that you get a slightly skewed distribution, that's essentially due to a projection effect. And that again is due to the stretching and basically the fact that the configurations are piling up in the tails and moving away from your original peak. And then, you know, it flattens and then and shifts a bit, right? Now, but this projection effect has a very distinct signature in the Lambda-CDM model, and that is the peak moves to decreasing omega m values with increasing effective redshift and increasing H0 values with effective redshift. That's the prediction of the Lambda-CDM model. Now, I'm going to show you that you get the opposite thing in real data, right? So which is already at odds with the Lambda-CDM model, right? So even and just to point out, yeah, the rest of the points are, yeah, if I guess stuff I've already said. Omega m, you injected a 0.3, it's going to move unless you combine those 2 constraints. And the PDF ultimately wants to just become a uniform or flat distribution at very large redshifts. That's because at that, you know, once you go to very high redshifts, then you can't disentangle H0 and omega m. They're just complete. There's an infinite number of values that would recombine into whatever your data is actually sensitive to, and it's just one effective parameter and not 2. Did cosmologists learn something from this? Was there any new information in this, or everybody knows this? Anyway, projection effects don't explain an increasing H0. Oh, they did a decreasing H0 trend, which is what we see in real data. Okay, so here's the claim. In Lambda-CDM, we have a decreasing, so conversely, a decreasing H0, increasing omega m trend with effective redshift in observed data. In mock data, you expect the opposite, right? And since S8 is proportional to sigma 8 square root of omega m, S8 also increases with effective redshift. That's what you would guess. This is naive. This assumes that sigma m is more or less robust. If omega m is increasing, then you expect S8 to increase. You could have a contrived scenario where sigma m increases and sigma 8 decreases and S8 stays the same. Either way, you know, all of these parameters need to be constants. If they're not constants, then your model is toast, right? That's essentially what's going on. So the claim is more, what's nice about this claim is it's more or less consistent with existing tensions. Adam Rees and various other people are finding that basically H0 is higher in the late universe, and basically if you take CMB, or even if you take CMB out, you know, and replace it with, you know, BBN plus BAO, you seem to find that H0 is lower in the early universe, right? And the same thing for S8. In the late universe, we find that S8 is lower than it is in Planck. And maybe this explains it. Maybe these things are connected, but there's no glaring inconsistency with what we're seeing in observables that define these tensions and what you would see from redshift evolution, right? So it's sort of complementary, but once you have redshift evolution, you know, the model just doesn't make any sense. It's just not predictive, and it's not physics, right? You can't work with a dynamical model that doesn't make predictions in physics. It's sort of pointless. Obviously, the Lambda-CDM model has broken down. So that's the claim, right? Now I'm going to give you evidence for it, and I'm going to pull this evidence from a whole lot of different places, and then, right, and maybe surprising places. So a question I've been asking myself, and I've been asking people. Sorry, yeah, go for it.
I mean, I just like to react to this. I mean, the whole point is that, I mean, I don't understand what you're saying. I mean, you're just saying that by binning in redshift, you find degeneracies and projection effects, which are perfectly expected. And now, well, maybe they're going to go in another way in the real data. And that's,
they go the different way in the real data. That's the point.
But for now, you're not proving that the model is breaking down. You're just showing that if you were to bin the data within this model,
right,
you should expect an evolution. But of course, the key thing is that by combining the various redshifts, you're picking up the redshift dependence. Not even talking of the fact that CMB is not only measuring angular diameter distance. I mean, that's just not true.
No, I would worry about CMB because it's only sensitive
but I'm just saying
to
that
angle.
Go ahead,
CMB. Okay. Let's back up a sec. So yeah, so all of this has been mock data. So these are statements about the Lambda-CDM model.
Right. Yes, absolutely. But
I've shown you nothing yet. I've shown you nothing yet.
Okay.
Other than there is a projection effect that leads to decreasing omega m and increasing H0s.
Yes, but you seem to be arguing as your claim that this could lead to what we measure as the sigma 8 or S8 tension and H0.
No, this claim goes conversely, goes the opposite direction.
Okay.
So already now I'm saying that's, you know, in real data we expect this effect. In observed data we're seeing the opposite effect.
Sure, but I mean, you've done mock data of DESI. I mean, what would happen with the real data that are much less constrained?
Right, and also these are PDFs, right? So I really can't say, you know, all I'm saying is that there's evolution in PDFs, unless you combine them, H of Z and dA of Z, and then we don't see any real evolution.
Mm-hmm.
But I'll come back to this point. There's things to be said about it. Okay, so let me give you the evidence, right? One thing that got me starting to think about this was strong lensing time delay. Strong lensing time delay has to assume a cosmology. They assume the Lambda-CDM cosmology because this gives them the most competitive errors, right? And then again, if you're doing H0 from gravitational waves, if you're doing it with, you know, binary neutron stars, that's fine. You're more or less agnostic to the cosmology. But once you look at binary black holes, you have the same problem. You are assuming a cosmology, and if that model works well, then H0 is a constant. But if that model doesn't work well, then H0 is no longer a constant, right? So, I mean, in some sense, the logic is kind of circular here. You know, when you basically, like, let's just take this on the left-hand side. This is basically from Wong et al. From the original Holly Cow paper and the follow-up with TD. Actually, this is from the TD Cosmo paper, the follow-up. Where the original this lens is added. So the original paper was 6, and there was a comment on a descending H0 trend across the lenses. This is basically the later paper where they look at systematics and they conclude there's no obvious systematic here. Now, essentially, the H0 has to be a constant, but yet we're seeing a descending trend in H0. It's not very significant. It's about 2 sigma, a little less than 2 sigma. So it's almost nothing. But if you build up a database or a set of like 40 constraints on H0 from strong lensing, and then we find that basically that descending trend is there, what you've actually shown is that you can't determine H0 in your assumptions. That basically, you're going to have to do a U-turn. And this comes back to the original argument, right? Is H0 a constant or not? We just don't know. And we need to check. And if the evolution is there, then the model just doesn't work, right? And just to point out recently that TD Cosmo came back to this particular data point and they reevaluated it using stellar kinematics and found more or less consistent results. Maybe their errors are a bit larger, but it just shows that the assumptions that they adopted in the original paper, the one from 2019, they were not so bad, right? They seem, if they relax those, they seem to, at least for this data point, the central value is more or less the same. The errors may be slightly larger. So it'll be interesting to see how this develops, right, as we move along. But there is at least one example of a descending trend of H0 with Z lens. Now, it's not the redshift of the source, but still it's an effective redshift for that system. Okay.
Can I react here again just quickly? I mean, what you argued is that if you've been in redshift, you cannot trust the posterior on H0. So this, I agree, like the fact that you're looking at high redshifts and you deduce the value of H0, maybe you can't trust the value of H0 because of degeneracy, in a projection effect or whatever. But that's okay. And then what you should do is actually combine these redshifts to measure H of Z essentially, and then deduce what is going to be H at Z equals 0.
Right, but you could always do this. You see what I'm saying? Like what the Holy Cow are essentially doing is drawing a horizontal line through this. When they combine their PDFs, suppose we had these PDFs, right? Yeah. We find that they're all shifted in Z lens, basically.
Sure.
You have built in from the beginning that H0 is a constant.
Okay, yeah, I mean, but
and that implicitly assumes that the Lambda-CDM model is correct. Now, if we go and look at what the motivation for Holy Cow is, it's basically to check whether or not H0 is 67 or 73. Now, why are they using the Lambda-CDM model? That model is.
But they can. I mean, you can let. So first, again, I think what you're showing here by being in Z is in agreement with what your mock data has shown. So it means that.
No. The mock data shows the opposite. Mock data shows there's an increasing trend of H0.
Okay, maybe it goes the opposite way in practice. That's okay. I don't know if these are as accurate as DESI data in practice. So the amount of information may not be exactly the same.
That's fine, but this is well documented.
The point is you can also just relax the cosmological model and allow for, I mean, this should be what you're saying, and I agree with you, is this is a good, in principle, a good diagnosis of maybe indeed the H0 is, the Lambda-CDM model has some redshift evolution, but then you can relax and ask, what if instead I have an equation of state that evolves or curvature?
You could do, right? But so some of the stuff in cosmology is like, once we start adding extra parameters, the errors inflate, right? So what's nice about working with the Lambda-CDM model is it's a minimal model, right? And you can see trends in it quite easily. So for example, if I take the same lenses and analyze them with the WCDM model, this descending trend disappears. If you look at the Holy Cow paper. Also, if I
so this exactly. I mean, this would mean that in principle, maybe Holy Cow has some support for evolving W. I mean, which I'm not claiming, but this is you've absorbed this bias in H0 by the fact that W is not -1.
Right, but I can give you an infinite number of cosmological models where basically the errors are 10% on all parameters, including H0, and there's no tensions.
Okay, I don't. Say that again.
You know what I'm saying? Like,
anyway, I should keep going with the talk. I understand what you're saying.
No, I'm not being annoyed. So basically, the rationale for probing the Lambda-CDM model is basically to understand whether it's breaking down or not. Mm-hmm. I'm just saying that this is the first result.
No, I mean, I think it's an interesting diagnosis tool. It's just that you're saying that on one hand, your mock data shows you that it should evolve, and then you get that it evolves. It looks like
but in the opposite way. Now I'm going to give you more
maybe in the opposite direction, but But you
This
should
is
also do
Exhibit
the
A.
amount of these things, you know, not okay.
I mean, this is the first exhibit. We're going to go through many of them.
Okay.
Okay, so we were interested in this. We built our own little cocktail of data that combines local and cosmological data. So this was Pantheon plus BAO plus CC, cosmic chronometers basically. And we binned it, and we found a descending trend, more or less at 2 sigma. It's cute, but very fishy, because basically our trend is driven by bin 1, and that's a mega maser. We took this mega maser result, which is 73 anyway. So that drives this descending trend, right? If we take away our bin 1, then you can more or less put a horizontal line through that. There seems to be a small drop off here, but we wrote the paper, and just to spell out what the implications are, it says that basically early universe modifications, including early dark energy, are just not relevant if you have evolution in H0 in the late universe, because these models assume they're tweaks, if you like, and then they assume that basically the late universe is the Lambda-CDM model. And if the Lambda-CDM model is performing fine in the late universe, there should be no evolution, right? So this was the punchline of our letter. But this data set, okay, it was a nice paper to write. It's cute. It's a fun paper. I don't expect anybody to buy this, right? Because you can just eliminate this bin. And this is sort of local data. This is all cosmological. There's a mismatch in data, but let's go on anyway. I came back to this idea because of a paper by Maria Dinotti et al., right? Actually, maybe not even because of Maria's paper, because of a later paper by Dominic Schwartz. But what Maria and a company had done, they wrote a paper in 2021 where they looked at the Pantheon sample. And then they took models like the Lambda-CDM model or WCDM model or whatever, and just basically assumed that H0, which should be a constant, they just gave it a Z dependence. So it's now a constant, and it has a sort of 1 plus Z and an alpha there. And they essentially fitted that, and then found that there was evolution through the Pantheon sample. Okay, so that was the statement in the paper, but they left it open. It was like, is this a selection effect? Is this something funny in the supernovae? Or is this, a modification of gravity? Or so it's sort of, they just left it open. It's an interesting paper and a very interesting observation. I should point out that what we missed here is Pantheon is built in here in the bin data, because when you combine samples, it's not obvious what's going on, and it's not obvious what's driving anything. We sort of overlooked this. So this is nice result. This is nice work. But what really caught my eye was a later paper by Dominic Schwartz, where Dominic Schwartz was actually studying the cosmological principle. So basically, he's interested in inferring the dipole from Pantheon, but he binned it, and basically he's looking at variations in omega m and variations in H0. And towards the end, the errors are very large, but what you see is basically H0 falls off towards the end, and omega m goes up to compensate. So this. Once I saw this, I was like, oh, then there probably is some truth to this, that there is evolution across the Pantheon sample. Now I will show you plots later where I show that evolution, right? And to stress, right, this is maybe 1.9, 1.7 sigma. This is about 2 sigma. It is independent, but driven by something, the first bin basically. This is, of course, this and this are not quite independent. You're looking at different samples where you're seeing the same signal at low statistical significance. But by combining samples, you can build up a picture where this is true. Now, to go a bit further, I'm going to take you now to quasars, which to me, I started working on quasars, and my first reaction to the quasar paper of Risoliti and Lusso, basically they wrote this paper in I guess, late 2018. And, it's very interesting. They've made an incredible claim that basically their high redshift part of their quasar Hubble diagram is inconsistent with Planck Lambda-CDM. Now, they did adopt a model-independent approach, right? And that model-independent approach you're never sure whether it's, the modeling that's basically giving you the result or it's the data that's giving the result. So I had a look at that back in 2019. And I basically convinced myself that this is a problem in the data. So it's not anything to do with their modeling, that it's essentially a data problem. Now, quasars are deeply challenging. Now, why they're challenging is because quasar Hubble diagrams are essentially high redshift Hubble diagrams. and you never know if they're standardizable or not. So even if you have a proposal for turning them into standardizable candles, if you talk to experts who work on supernovae, they will sort of say, yeah, you just can't trust this, right? And that's fair enough, right? People are entitled to their opinions. So this is either trash, and I picked the word trash. Thomas made me laugh in a recent talk where he described type 2 as trash. He means in the best possible way, like, do we trust it or not? Or new physics beyond the Planck Lambda-CDM model. And basically, what's happening here in this Hubble diagram is basically, magenta is essentially the Planck Lambda-CDM. What you're finding is actually a fall off in the distance modulus at high Z. Now, what they've actually done in this paper is that they've calibrated their quasars with supernovae, which are in cyan, right? This was the JLA data set, right, in the original paper. And basically, this fixes the Hubble diagram up to, say, Z equals 1.4. So we're not sure what's going on up to Z equals 1.4. It's just basically consistent with the supernovae, and the supernovae are consistent with Planck. And then basically the deviation becomes it becomes evident at a higher redshift. So that's the claim of the paper. There is a departure at high Z. This is more or less what their data looks like. Log, basically the log of luminosities in X-ray versus luminosity in UV from quasars. There does seem to be a line there. There's an awful lot of scatter. The gray is essentially their original set, and the yellow is basically what's whittled down after whatever cuts they take. There's still an awful lot of scatter in it. I've been using the later sample, which is a larger one, and I've been working with that. But these are essentially the claims from the original papers. Okay, now what surprised me about the RL quasars is that there is actually evolution in omega m through the whole sample. So if you take the quasars and if we make them uncalibrated, which means I don't use the supernovae to set the scale. So I can't determine H0. I can determine omega m though, and I have some other nuisance parameters. What you find is that if you fit the quasars between Z equals 0 and Z equals 0.7, you have a sample of maybe 400 quasars, right? Did you find you recover a Planck value, a best fit that's more or less consistent with Planck? And then as you increase the redshift range, which is increasing the effective redshift of the sample, then basically that omega m ticks up and it basically goes towards omega m equals 1. Now, what the plot on the left-hand side shows you is basically it's an MC-MC exploration of basically this first bin, which is between Z equals 0 and Z equals 0.7. And you more or less find a peak in the right place. So it seems to agree with the supernovae. Yes, okay, omega m is 0.3. But then as we move up and change the effective redshift, then it sort of moves through, right? Right, good. Now a caveat. The caveat here is basically that in the original paper, or at least in this later paper, the authors basically say we shouldn't use the quasars below 0.7. We shouldn't use them for cosmology, right? But we have used them for cosmology. We've basically just fitted them. They're part of the sample. The authors would prefer you cut them out, but they're there. You can use them, you can fit them, and you find 0.3, and then 0.4, 0.5, 0.6, so it goes in that. So there's an evolution through the omega m in the sample. And so now the question you need to be asking yourself is like, okay, if in the same redshift range we agree that omega m is 0.3 in quasars and supernovae, then the quasars are less crazy, right? We've got some support here for the quasars doing something reasonable, and they're not just complete trash. Now, what we want to see is that evolution there in Pantheon supernovae, and the answer to that is yes. As Maria and her collaborators had shown, there is a descending H0 trend. Now, there is a slight difference here between supernovae and quasars. Quasars are intrinsically high Z. It's very easy to find high Z quasars, whereas supernovae are intrinsically low Z. It's easy to find supernovae at low Z. As you go to high Z, the samples become sparse. So to create a sample with a higher effective redshift, what you have to do is start removing supernovae at lower redshifts. So what these pictures actually do, or these plots do, is they impose a cutoff. And then we start removing supernovae below a Z min. And so when the Z min is at the 0, we have the full sample. And as we go through it in sort of intervals of delta Z, whatever, there does come a point where basically H0, the central value, decreases. So this is essentially the effect that Dominic Dominic noted here, and that then Maria had noted in her earlier paper.
Sorry, I mean, the supernovae, you don't know what the value of H0 is, right? So what have you?
Right. So good. Thanks, George. So the supernovae are uncalibrated. So we fix them to a constant, and that means that there's no errors that are being propagated in M. Okay.
So you've just fixed the Planck value at low redshift. Is that?
No. So here H0 is just we just fixed them to a nominal value to get H0 to be 70 for the whole sample.
I see.
We could have picked any other value, but 70 is a good number, and so it's H0 in quotations, right?
That's what's assumed in the Pantheon catalog.
Right. So it's very reasonable from the Pantheon paper perspective, right? But there is evolution in the central value, but because the statistics are not good at high redshift, basically our errors basically eat up that evolution. These are 1 sigma confidence intervals. And we did some mocks in the paper, the original paper, and made a comparison, and more or less it's a 1 sigma thing, right? So nothing really to see too much, right? But again, it supports a narrative where quasars are doing one thing and supernovae could be doing the same thing. And again, it's a descending H0 trend, which is opposite from what you expect in the mocks, the DESI mocks, right?
Yeah, but again, it's not clear to me that we are measuring and modeling the same thing. I mean, spontaneously, if you're measuring large redshift, where only matter matters, you should measure omega m equal 1. It makes sense. If you're not seeing the break.
No, there's no statement about that. Let's go back to our mocks.
But here, I don't exactly know what your mocks are doing. You're actually having large redshift range from 2 to 3, maybe for some.
Right, but let's go back.
Some redshift dependence, maybe something is. I mean, all I'm saying is, from
a year ago we thought this. Now I don't think this, right? So basically my feeling as well was, I'd listened to these arguments from cosmologists and I was like, oh, omega m must go to omega m equals 1, right? But you can't prove that. All you can show is that basically as you go up in redshift bins, you just become insensitive to dark energy density.
Right.
Of course.
Now, but that doesn't tell you omega m is 1. That basically tells you that B is more or less well constrained. There's no way you can now the only way that H0 can be disentangled from omega m is through fitting the data.
Sure, I mean, but what you're showing me from the supernovae is exactly what I'm expecting. You're going to very large redshift, and you may expect on H0 and omega m blows up, and there is nothing inconsistent with lambda.
No, I agree. The errors are blowing up. Fine. So that's basically.
And then I mean the projection goes one way. I mean, if you had an analysis of mock data representing what you're doing here, maybe it would have blown. Maybe the shift would have been go towards higher omega m. Here, I don't know why in the case of DESI it's going towards low omega m.
Okay, but let's agree the central values have gone up. The best fits go up. So for H0 they go down, omega m they go up.
Sure.
We just don't know. We don't know if they're now consistent with Planck or inconsistent. They're consistent because the errors are large, right?
Yeah, but at the same time, this is not really. I mean, what matters is the redshift evolution that Lambda-CDM is able to reproduce. It's not just at high redshift when they. And I don't know. I don't think
you need to think about it.
I'm amazed by the fact that at one redshift,
email, right?
Sorry.
Let's think about it and let's discuss it over email, right?
Okay.
So basically, now there's a question now. Suppose W1st Roman Space Telescope is going to come. They're going to find more supernovae at high Z, right? Are these error bars going to contract to the Planck value, or are they going to contract to a different value? This is a very valid question. At the moment, the central value
you could have infinite precision and still, in fact, have since you're measuring one parameter, one quantity, have an infinite error bar on H0 and omega m. If you're focusing on a single redshift, which is what you're doing with this game.
No, I'm not.
No,
wait a minute.
Extremely precise H of Z at that.
Sorry, this is the Pantheon sample between Z equals 1 and Z equals 2.26, and we're fitting it. So there's like 24 data points or whatever it is, right?
Sure. I mean, that's maybe it affects a little bit my argument, but if you're in
the statistics are, those 24 data points. Now, if you can now populate between Z equals 1 and Z equals 2, and you inflate that by 100 times, we can basically shrink those errors.
Okay, yeah, I mean, I guess that
Now, where are they going to shrink
you have
to?
lever arm, but the key is the lever arm again. Huh? It's the fact you're using lever arm between Z min and high Z. If you just have one redshift, it doesn't matter.
No, these are not one. This is the lower
Can I
bound.
make a
So
comment?
yeah,
I mean, I'm pretty much in agreement with what Vivian is saying, because it's really you expect a total degeneracy between the way that you're doing it between H0 and omega m if you look at high redshift data.
no, that's okay. Let's go back to this.
So, well, wait a
Let's
second,
go
let me
back,
finish my- let me
George.
finish my
George,
point. Let me finish.
this is the bottom point here. The PDF ultimately becomes a uniform or flat distribution at very large or infinitely large redshifts. We agree on that, right?
I don't know if it has
finite
to be
redshifts,
infinitely large
there-
redshift. I mean, what matters is the lever, the redshift dependence. I mean, if you're measuring the prediction of Lambda-CDM is omega m 1 plus Z 3.5. If you have a lever arm of that function, or not. I mean, if you have a very
I don't know
narrow,
what you mean by lever arm, right? So let's go back to this.
you need to
plot
measure
then,
1
right?
plus
Let's-
D3
Let's
half.
go. Let's agree on something. There
Yes,
is a
yes,
peak
go ahead.
here in the red.
Yes.
Where does that peak come from?
I'm guessing that it's coming from the fact that you're measuring some redshift range from 2.3 and 3.6 with fairly high accuracy that allows you to reconstruct a shape of h of z that is compatible with the law 1 plus 1 plus z 3.5 that is associated to the behavior of matter. And then the overall normalization degrades,
Right. Still, these are words. I don't understand what you're saying, right? So there is a peak here,
Yeah.
right? That peak was injected because we basically fixed the input parameters for the mock. Now, if there is a degeneracy, and that's an absolute degeneracy, I can't disentangle H0 and omega m. That means there's no memory of H0 and omega m. That
Yes,
means the
absolutely,
distribution is flat.
Yes, absolutely.
Do we agree on that?
Yeah, absolutely.
So there is a peak here. So there's a residual in the data.
Mhm.
So I still don't understand what you're trying to say.
What
Basically,
I'm saying
as
is
you go up
are
in
not
redshifts,
only okay.
you can determine best fit parameters for H0 and omega m,
Mhm.
except the errors are large.
But why would you want to do something like this? This is what I'm saying.
George,
okay, so
because
look,
George, let's go back to science,
No, but can
right?
I-
You're a scientist.
Please,
And-
can I give my point of view? Okay, then you can count.
Let me go back here, George. Let me go here.
At least let me speak. Let me say something.
Okay.
Okay, I mean, all I'm saying is that I think that this is misusing the data. It's using the data in a funny way. That if what you want to do is to test Lambda-CDM, then you need to remove degeneracies. So I mean, a much better thing, if you're worried about omega matter at high redshift, look at the recent AX lensing results, which are spot on Lambda-CDM. And
Okay,
exactly this high redshift range. They're sensitive to this high redshift range. So you look at experiments that target the redshifts that you're interested in, and you test for consistency of Lambda-CDM.
Right. But George, still,
I just don't see
fine.
the motivation.
Lensing still has to go through these degeneracies that you're worried about, right?
No, I mean,
the descending H0 trend here. Now, either the error bars are underestimated in all of these inferences.
Okay, all right. I've made my point.
You've made your point, but basically, are you criticizing what Holly Cow are doing?
Yeah, well, I'm criticizing what Holly Cow are doing, but for very different reasons. Okay, because as you know, I mean, you showed the results which had a correction for the external shear. Okay, this is a real big problem with any lensing. With any time delay measurements, because there's a complete degeneracy. You're basically measuring h times 1 minus kappa. Okay, so you've got a complete degeneracy, and there are two ways that, I mean, you can break out crudely.
But I still don't understand what cosmologists understand when they say about degeneracies. Are you saying you can't do least squares fitting?
Well, no,
are you saying, like, this is the weird thing I have? Let's forget about the errors. Yeah. We have a chi-squared, and we can we extremize it. Are you saying that basically the extremum of a chi-squared is ill-defined?
No, I'm not saying that at all. I'm just saying.
Good.
That
So
when
you're a
I've got large-
scientist, George.
when-
This is
when I've got-
great.
When I've got large degeneracies, I look to get, supplementary data, additional data that will break the degeneracies.
Right, but George, what you're implicitly assuming in the background is that there is a model with constant parameters when you break degeneracies.
No,
Now,
not at all. Not at all. Not at
okay,
all.
let me move on. Let me move on and we come back to this, right? So let me just concede here that basically the errors are large and everything is consistent with Planck, but there is evolution in the central values. Now, the central values are the best fits. They're the extremums of chi-squareds. So, mathematically, this is just well defined. The errors are large, though. Are we all okay with this?
Yes, but in principle, you could imagine that the chi-square is relatively flat in that direction. So that's what is
Could be. But then we would estimate errors, right? And then the errors would be large, right? Or you do an MCMC exploration, the errors would be large. It's fine, right? These things are all, if you have degeneracies, you expect large errors. Is that okay?
Yes, absolutely.
I'm not making a claim based on the central values for the moment. Now, this is something we did. We took these samples. We took the Pantheon sample. We took observational Hubble data, which included BAO and cosmic chronometers. And we took the quasars, right? And we imposed the prior on omega m h squared, which is basically saying the prior we got from Planck. So that's basically fixes the upper part of the Hubble diagram, right? So that's all it's doing. It's basically providing guidance to that. And what we did is we fitted the full sample. So the one here on the left is basically the observational Hubble data. And we've got 54 data points, and it's in a range 0 up as far as 2.36. The 2.36 is essentially Lyman alpha. We know it's mildly discrepant with Planck Lambda-CDM anyway. Fair enough, right? But these are the values you get over the full sample. Now, then what I'm doing is basically the game that I've been playing with the Pantheon sample. I've been increasing the effective redshift of the sample and only looking at best fits. Now, again, in my mock data, the best fits, because of projection effects, H0 has to go up and omega m has to go down, right? Those were distributions based on best fits in the DESI mocks. Here we're finding the opposite trend. And what this probability is basically is the probability of, if I constructed mocks in the same range. So basically, if I take these data points, these 28 data points, and now impose the central values or the best fit values for the full sample, the question is how often or what probability, with what probability do I find a larger value of omega m in my mocks? And basically, if you don't move very far, right, then, basically if we cut out only a small bit of the low Z part, we look at, a subsample that more or less is most of the original sample in terms of redshift, then the probability is very, it's quite large that we would find something randomly that would basically give us an omega m value that's, 0.294, given we had 0.299 for the full sample. But I mean, as this guy ticks up, the probability goes down here, right? So what I'm doing is, again, transporting these guys and using them as the basis for mocks in the same redshift range, and then making a statement about, how often through a random fluctuation or whatever, do I basically find omega m's that are larger or H0s that are lower? And so this on the left is the observational Hubble data. This is the Pantheon sample. And this basically is the quasar sample, where things go the opposite way, where basically over the full redshift range, I basically have an omega m equals 1. And that's why quasars are so deeply challenging, is basically they sort of tell you that omega m is 1, right? You either just sort of say, well, omega m is 0.3. Everybody knows it's 0.3, and these guys are just complete junk. But they're also a high redshift observable, right? So again, in the quasars, what's going on is these look like crazy numbers, but they're basically coming from the fact that I've imposed a prior here. So this times this has to add up to something, or basically just has to give a particular number, the Planck number, right? But I mean, no matter how you look at this, you're looking at evolution in all of these samples, right? So this is just a particular snapshot of the mocks in a given redshift, what you get from the real value, which is off here. This peak should have probably been a little bit to the right because it's essentially mirroring what we saw in the DESI mocks. But again, you're seeing, your mocks are basically, you have these non-Gaussian tails. So, and then this pile up here is just for my bounds, right? But basically what we're doing is counting you know, the number of mocks, you know, number of best fits we find out here versus the number of best, you know, the number of mocks in the full sample, right? And then we give a probability for basically getting a value that's the same as the real value or larger, right? And sometimes we saturate the bound here. I haven't imposed, you know, anyways, you can work through these probabilities, it's fine, right? So there is evolution in these samples, right? And it's low, it's like 1 to 2 sigma in each of them, but they're independent. And then you can combine them using Fisher's method and you get 3 sigma. You get 3 sigma for evolution through these samples in the Lambda-CDM model. Okay, now here's Pantheon Plus, where you do the same thing, but now what we're doing is basically pulling the sample apart in 2 parts. So if we go back to Pantheon, here I was basically just focusing, I was throwing away the supernovae at low redshift and just fitting the supernovae at high redshift above a Z-min. Now here I'm basically splitting the sample, right? And I'm using whatever supernovae you have in Cepheid host galaxies as calibrators. Okay, now, so there's 77 of those, and Pantheon Plus is like 1,700. So there's roughly 660, just over 1,600 supernovae that basically you can use to determine H0 and omega M once M itself is fixed. Here, M is actually, you know, everything is calibrated, right? So you're propagating errors in M, and you find the same thing. You basically find that at higher redshift, we took Z to be 1, that basically your H0 value, let's see what's going on here. Oh, sorry, and below Z equals 1, yeah, so that's below Z equals 1. That basically the H0 value is consistent with what you'd expect. It's more or less the 73 or whatever you get from the Pantheon Plus sample. And then depending on your priors, so we've taken different priors on omega M here. We just wanted to relax the 0 to 1. What you find is you find like basically the peak is beyond omega M equals 1. The peak of your distribution in omega M is basically, you know, the high redshift part of the punchline is basically the high redshift part of the Pantheon Plus sample. If you separate it from the rest of it, it prefers omega M greater than 1, which is essentially what we're seeing in the quasars as well, right? So again, it looks like there's evolution through this sample as well, right? And it's not surprising. We see it in Pantheon. We see it in Pantheon Plus, more or less what you expect, right? Except now we propagated errors on M. Now, if you buy into this, or if you take this, let me just finish up very quickly. You would expect evolution in S8 as well. If omega M is evolving, S8 has to evolve. Now, here's a very simple thing you can do. Take constraints for F sigma 8, right? Let's assume, as most cosmologists do, that basically omega M is a constant. Let's fix that to the Planck value, you know, impose a Gaussian prior on omega M 0 or something equivalent to that. That basically fixes omega M. It's almost like basically making omega M 0 a constant. Now, then the only parameter that you're really sensitive to is sigma 8. So, you know, sometimes we talk about S8 tension, sometimes we talk about sigma 8 tension, and then fit it to samples, right? And what we're going to do is play the same game. So we're basically going to split the sample into a low redshift part and a high redshift part and see what happens. In this paper, we basically used some data that Dragon had recently compiled with collaborators. It was like 20 data points of F sigma 8 constraints, and we split it and we showed that there's evolution in S8, which is essentially sigma 8 because omega M is a constant. And then we used a larger sample that's due to Leandris and his collaborator, but this overcounts data points, right? So basically, you know, this is an overcounting of data, but again, you find the same evolution. And so what we actually find is that as we look at this Z-min, so here I'm basically doing the same game that I played with Pantheon Plus. I'm throwing away data in this sample of 63 data points. And as I throw away the lower redshift data and just fit the function that I have to fit, then I find that S8, which is essentially sigma 8 here, is evolving from a lower kids DES type value into a Planck value and then beyond, right? So there's evolution again in S8. Now, there's the data is, the errors are underestimated here because, you know, these data points come from essentially, well, maybe, you know, the same surveys or reanalysis by different groups. So we're overcounting data points. But basically what's driving this whole thing is that at a higher Z here, that these data points are largely above the curve, right? And the whole, as you basically cut out the lower part of it, then these get pushed up, right? And that, you know, leads to an increase in sigma 8, right? Again, looks like evolution there. There is claims by Matteo Viel and collaborators that there's evolution in sigma 8 between low Z clusters and high Z Lyman alpha at 3.3 sigma. So it's not the same observable. It's not the same. I mean, okay, here it's largely RSD. Maybe there's a bit of peculiar velocities in it. You may worry about systematics there, but again, it's the same trend. So it's an evolution that you're seeing in sigma 8. Let me just give the summary. Yeah, okay. If you're a scientist, right, and you work on dynamical models and you have fitting parameters, you need to be careful that your fitting parameters are constants, right? Right. So basically, in the Lambda-CDM model, those fitting parameters are things like H0, omega M, S8. Essentially, they're integration constants, more or less. Mathematically, they must be constants. If those guys are evolving, then your model is breaking down. It's as simple as that. Redshift evolution is non-negotiable, so we can't debate this. These tests can be done. They're done all throughout science, right? Cosmologists are not doing them. Now, cosmologists are basically saying there's degeneracies and we shouldn't do stuff like this. They're basically saying that your errors are too large, but yet the errors can be quantified, right? You know, MCMC allows you to quantify errors even when you have degeneracies, right? And you may be able to split your samples in two and find that there is no longer overlap, right? Or, you know, just confirm that there is evolution through your samples, right? Evolution in the late universe eliminates lambda as dark energy, right? So basically, if omega M is moving, then you're looking at energy is moving between the dark energy sector and the matter sector in your model. And of course, everything's, you know, they should be constants. This disfavors new early universe physics. In none of this, there's a length scale. There's no length scale. Like, tweaking a length scale is the simplest thing you can do. When you add new physics, you have to adjust an equation of state, right? So if there is evolution, you can't just fiddle around with a length scale. You really need to go after the equation of state. You need to construct a new model that would address that evolution, right? So what EDE is actually motivated by is changing the radius of the sound horizon, which is essentially a length scale. That's a small tweak. Even though it does inject new physics, it injects new physics, you know, pre-recombination. That's difficult to test, right? But still, we should see the evolution, right? This is, you know, for doubting Thomases, we need to see the holes in the hands. That's what we need to see, and we need to see the evolution to make sure the Lambda-CDM model is breaking down. Quasars, if standardizable, again, big question marks over this. They've already shown us so much. You know, they seem to agree with supernovae on 0.3 at low Z. They seem to show evolution through the samples, and the evolution is more or less the same in supernovae and in quasars. I really feel that they're not telling us that just that dark energy is not lambda. They're telling us that basically there's a proper problem with the assumption that basically matter density scales as a to the -3. And that's something that we should really have a look at. And then now, if you buy all of these results on the basis of all of this, right, and we feel that, you know, the high Z part of the Hubble diagram, even in quasars or whatever, is not really Planck Lambda-CDM, then, you know, JWST anomalies, of course, you know, your cosmology is in flux, and why wouldn't you have anomalies in JWST, right? Let me just finish on that. Any questions or comments? Whew. Eleanor, are you still there?
Yes.
Okay, good.
Thank you so much for the seminar. Any questions?
George, just to get back, if any questions before we get into that.
George is not here because I think he's late. So I have one question actually.
Right.
In your simulations, when you simulated the DESI data, okay, how many data points are you considering?
29 in total, right? Whatever's here. But they're binned according to, you know, they're in bins of 8. So the first is 8, next 8, next 8, and then 9 in the last bit.
Okay, so this is not consistent with what you see then in the data. So
no, I'm just saying that basically here the underlying assumption is the Planck Lambda-CDM model.
Yeah, but if you have few data, so it's normal that you can't see exactly the same behavior. So
no, but I mean, we recover the input parameters at low Z, right? And so what's happening there, you know, you know, even with 8 data points, you can still get back the Planck Lambda-CDM model in the right bin.
No, because you lose completely the constraining power. So you can, that is why. So here you have a good constraining power because you decided which is the number of data points that you have.
No, but in each of these bins, there's 8 data points.
Yeah, but at the end, when you show the same for the real data, you have like 28 data points in one bin and 6 data points in another bin. So they are not consistent.
No, but the point is that there's evolution. I'm trying to show that there's evolution through the
Yeah,
sample.
but I don't see the evolution because if I have just 6 data points compared to 28, okay, I don't see the evolution. This is just
No, I mean, the evolution is not in the data points. The evolution is in the fitting parameters, right?
Yeah, but also here, if I compare omega m that is 0.4 plus minus 3 with the latest one that is 0.7 plus minus 2, okay, they are consistent, so I don't see evolution.
Right, but do you see evolution in this?
No, I don't see evolution in that because this is
the
consistent
claim
within
of,
one error bar, within one
right,
signal, so I don't
right,
see evolution.
the claim of the original paper here is that basically the high Z part of their Hubble diagram is in 4 sigma tension with Planck Lambda-CDM.
Yeah, but if you go in the next slide, I think, like the next one, there is a certain point where you just show the best fit of the data.
This is best
Yeah.
fits, right?
Exactly.
But okay, let's back up a second. This is evolution in best fits.
If
Yeah,
you-
but it is not an evolution, okay? Best
if
fit
you're in-
doesn't mean anything.
Right,
If you're
okay,
interested
but
in
let me
chi-square
go forward
statistics,
one slide.
look into profile likelihoods. Do a profile likelihood as opposed to
That's what
using
this is.
MCMC method.
This is what these
No,
guys are.
this is
These are
not a
basic.
profile likelihood.
What do you mean? This is a PDF.
It's not a profile likelihood. What you're showing me is a posterior distribution, or it's a PDF of the chi-square of many different mock
Right.
realizations.
There's no one realization of data.
So it's-
That's based on
The
it.
point is, for a given realization, if there is a degeneracy, which there will be, you will find that the profile likelihood of your given realization is very flat. It means that in reality, you can find many values of omega m and h naught that give you values of chi-square that are within,
that
delta
are
x
close.
of 1
That's
typically.
fine, Vivian. That's close. But
So,
you know in mathematics you have an optimization problem, right? When you minimize something, you can get a unique value, right?
yes, but this is not what error means.
No, that's not the error. That's
when
the
you
best fit,
quantify
right?
an
No,
error,
wait.
you don't
Vivian,
only
back up
care
for a sec.
about the
Right.
best
Okay.
value.
For Cosmo, let me explain. So,
Okay,
the extremum of a function is unique. Would you agree with that?
My point is that, sorry, my point is that mathematics and physics are 2 different things. Okay, in physics we have error bars, so we can't just say the value of one parameter is moving in one direction. We have always to quantify with the error bar.
No, that's fine. No, but Eleanor, to be careful about this, what cosmologists actually do is estimate errors. Best fits are unambiguous within machine precision. They're the extremum of a chi-square.
Do a profile likelihood and check the length, how much the best fit
This should have been easier for you guys. Basically, this is the Pantheon Plus sample, separated in independent subsamples.
And this is making a lot of sense. What you're saying is at very large redshift, you're losing complete sensitivity to omega d, and omega m goes to 1, and you're extremely sensitive to your prior.
No, omega m has gone beyond 1.
Yes, because you're becoming your prior, whatever. You're becoming your prior, and this is making complete sense. I don't understand.
Where am I becoming my prior? There's the
you're
prior
showing
here
me that as you have a purple, or as you change the width of your uniform prior on omega m, the width of your posteriors.
Good, I agree with that. Right.
So this is exactly what I expect. I don't know what happened.
No, but where is that increasing?
But this is exactly what I expect.
Is that increasing on the right-hand side or the left-hand side of this distribution? As I increase the priors, I'm finding spread in the right-hand side.
Yeah, and this is good. This is what I expect. So it means that I don't exactly know what you did in your mock, and I'm guessing that
there's no mocks here. This is just a split of the Pantheon.
I'm talking of DESI. I'm just saying this
real data.
What you're showing now is perfectly consistent with Lambda-CDM and my naive expectations. There is nothing.
Right. You could say it's perfectly consistent, but you do have a fall off here, right? That's not you.
But then there is projection effect happening. I don't know exactly how this thing.
It's not a projection effect, Vivian. That's the point. Projection effects tell you that omega m, this again, Projection effects, because this banana has to
You're showing
stretch,
me, yes, but this is what I'm
configurations build
it is
up
log
here.
data that is different from, it's a different prior and it's a different mock data. And you're claiming that what
No,
you're
no, wait a minute.
saying
No,
can
wait
be
a minute.
applied
Wait,
one to
the
one.
prior here is
By
different. The prior
Yes,
here
so,
doesn't
so
make
you
any-
can't make a conclusions based on this of what you've done with a different prior and a different data sets of the value of the effect of
Fine, right. No, wait a minute. This is mock data. It's generic.
Yes, it's not generic. Wrong.
Why would you say
Completely
it's
wrong.
not generic?
It's absolutely not generic. The mock data that you model, you have a number of mocked bins. You have a width of the error
I
bars.
could
You have a
change the bins,
correlation.
yes.
You can take very different mock data and get, just based on, I'm saying the accuracy.
No, wait a minute. Let's forget about the details.
The accuracy, I'm saying.
Cosmologists are buried in the details all the time. Now, do you agree, as I go up in redshift bins, that I become less sensitive to dark energy density?
100%, yes.
You agree with that? Now,
Yes.
do you agree that B becomes better constrained?
Yes.
Okay, so we agree on this then. Now, do you agree with these plots, right?
Yes, I agree. I mean, yes, I agree with the plots that you're showing me. Fine, they're
Right.
what they.
So, I mean, we don't have to do the analysis. You don't have to look at what bins or what width or anything like that. We agree where these things come from. We know, we expect them and they're there. But whatever effect you're seeing in the PDFs is a shift towards lower values of omega n.
I'm sorry, but I don't see the shift. They are consistent, completely consistent.
No, I mean, it's a shift in the peak of the PDF.
Okay, but the peak
What
doesn't
I'm-
mean anything.
No, that's fine. But Eleanor,
the
right,
other
let's
part.
look at it this way. These distributions are different. So basically, if
No, for me they are the same. Okay, because I'm a physicist, so I don't see the number.
no,
doesn't
no,
mean
let
for
me give
me.
you, let me
For
tell
me,
you
the
what's
error bar
different
means
about this.
anything. So I see that they are completely
No,
consistent.
Eleonora,
We're
you may see the
consistent with
same
your mock
thing.
data set.
What this one shows me is that basically there's no probability of getting omega m equals 1 in the low redshift bins. That's a statement I can make. Probability 0 for omega m equals 1. Here, potentially here, but here it's different. There is a finite probability of hitting omega m equals 1. These are not the same PDFs.
Eleonora,
Cosmologists
can I
argue
ask
they
something?
are.
But
It's just-
Yes, please.
Can I
it's
ask?
insanity.
Can I say?
Can I ask something?
Yes.
Okay,
I got to
so
run in 5 minutes, but yeah.
yeah, well, no, it's just a quick question. So, I mean, my question is the following: if you use other tracers of the Hubble relation, such as GRBs or H2 galaxies, do you get the same results as far as the
No.
evolution of
Good question. Now, GRBs are, the data quality is more or less the same as quasars in terms of errors, but the statistics are an order of magnitude less. So GRB samples are in the 100. Quasar samples are in the thousands, right? So we don't really see much in GRBs, right? But the data quality is poorer.
Okay, what about H2 galaxies? H2
So
galaxies.
I haven't looked at H2 galaxies, and how the question is
because they cover if I remember well, they cover the same area. I mean, the sample
Good, yeah. No,
is
they will
pretty good within redshifts between 2 and 3. So
good, but so you're going to need a large sample, right? If the errors are large, right? If they're scattering the data, you're going to need large samples, right?
okay.
If you have poor quality data, you're not going to see this evolution, right? Let's go back to Holly Cow, right? If the Lambda-CDM model is breaking down and your errors are very large, you won't see it. If we inflate all the errors, you don't see anything. So basically, you really have to have good quality data to start seeing this stuff. Pantheon, I'm arguing that basically there's evolution in Pantheon in the central values. The errors they're large enough to accommodate the Planck value at 1 sigma. That's fine, or the Reese value at 1 sigma. In Pantheon Plus, it's a little bit, you've got more statistics, it's a little worse. And we really need to build these samples and we need to check, right? Is there evolution in them? It looks like evolution to me.
Yeah, okay.
It's evolution in the best fits. And then it's just a question of how large are the errors. And if you have enough statistics, your errors shrink onto the best fits and you see a discrepancy.
Okay. Okay. I mean, I'm just saying that it would be a good thing to see if you include in your analysis, also additional tracers to see what is going to happen. This is a,
I agree completely. I agree. No, GRBs I've had a quick look at, they haven't worked in the sense that I don't see the evolution, right? But you're going to have to then stack those observables by data quality. I mean, the best observable we have is essentially type 1a supernovae. So if quasars were giving inconsistent results with type 1a supernovae, then quasars are just junk. They're sort of trash. You just can't trust them. Right? Now, you could sort of say supernovae tell me omega m is 0.3 and quasars tell me omega m is 1, and that's inconsistent and quasars are trash. But I think that's too quick.
Enzo?
Anybody else question? I'll try to answer quickly.
Yeah, sorry. Can you
Vivian,
show again your
We'll do emails, right? Okay.
your results, the prior results with DAISY?
Yes.
So before claiming that these are physical, I have a question. Did you base this only on one single random simulation of mock data?
No, so basically it's on 10,000.
On 10,000, okay.
So basically, again, so these PDFs are best fits. So you're building up a PDF of best fits, and each time you're changing the realization of the data.
Yeah, but it might not be simply that there is, because the errors, the dispersion is larger, the errors are larger, and then there is a bigger deviation.
There is a factor here. If you read our paper, well, okay, it's difficult. So one thing that I would expect here, let me just point it out, right, is that as you go up in redshift, you expect B to be more and more constrained. You can see that basically the Gaussian is tighter for, red over orange, but then these two are reversed. Okay? I would expect blue to be outside of green if everything was uniform. But it turns out, if we go back to DESI, let me go back to DESI, that actually there's an improvement in precision just about here, just at the bottom of this bin at 0.8. So if you look at the DESI forecast, you will find that some of their smallest errors are here. And so this just impacts. There's a difference. Yeah, I'm just saying that the data quality across this sample is not uniform. But otherwise, we would expect this trend. B becomes better constrained. A becomes less constrained. What was the question?
No, nothing. Okay.
Right. Anybody else? Send me an email, right? It's better to discuss this stuff over email, and we can do it slowly. And I'm going to email you guys anyway.
Okay, so
But Eleanor, thanks very much. And of course, Lisbon, we can tear this apart in Lisbon.
Okay.
And have long discussion sessions, right?
Thank you. Bye-bye. Bye.
All right, thanks. All the best. Bye-bye. Thank you.